Now, using these equations to solve the problem above here, we will see that from the question, electrons, I'll start from here. Solution. Number one, you will see that electrons were ejected when a wavelength, with a light of wavelength. So we have to actually state the parameters. The wavelength here of the wave is given as 5 times 10 raised power minus 7 meters. And then we can ask to find, from the first question, we can ask to find the frequency of light. The frequency of light, which is F, can be gotten as what? C over lambda. This is the lambda, this is the wavelength. And C, which is a constant, is actually a constant which is called speed of light. C is the speed of light. Speed of light, or speed of radiation. Speed of light. And is a constant, which is equals to 3 times 10 raised by 8 meter per second. Now let's quickly solve the problem over there. I'm going to rub the board off. I believe you have seen what is on the board. I'm going to rub the board off so that we can solve the first problem. The first problem, which is to determine the frequency of light, is F is equals to C over lambda. As you can see, the speed of light, which is a constant, is 3 times 10 raised by 8 meter per second over the wavelength, which is given 5 times 10 raised by minus 7 meters. You would realize that these are given in standard forms, and it makes it even easier for us to solve. If you use 5 to divide 3, which are the main numbers here, you have 0.6. And then if you use 10 minus 7 to divide 10 raised by 8, you have a very simple mathematics which can be gotten as 8 minus or plus. Now becomes plus 7. The meters cancel out each other. And then we now have 0.6 times 10 raised by 15 per second, because it's going to be over second, per second, per second, per second. That is all 0.6 times 10 raised by 15 hertz, or 6 times 10 raised by 14 hertz. If we remove the decimal point and move it forward, sorry. That is the solution to the first question. The second question says that what is the energy of the photon? Obviously, you will have noticed that from Einstein's postulation, he said that the energy is directly proportional to the frequency, and that the energy, the magnitude of the energy itself, is actually the product of the Planck's of a constant and the frequency of radiation. This constant is known as Planck's constant. Planck's constant. Let me quickly rub the board off on this side too. So 2. What is the energy of the photon? The energy of the photon, E, is actually the product of a constant and the frequency of radiation. The constant, which is Planck's constant, is giving us 6.6 times 10 raised by minus 34 joules seconds. And since we have found the frequency already here, it means that the energy of the photon is actually what? 6 times 10 raised power 14 multiplied by the constant 6.6 times 10 raised power minus 34. This is in seconds, this is per second, sorry, and this is joule seconds. You realize that the per second here, we cancel out the second here because they are inversely proportional to each other. And it will now give us a new value as the the energy of the photon, which is 3.96 times 10 raised power minus 19 joules. Yes. And then finally, we are supposed to compute the maximum kinetic energy of the photoelectrons. And earlier on told you that Einstein said that the ejected electrons actually moved with a particular speed and possess the particular energy which is called the kinetic energy. And this kinetic energy of the moving electrons is gotten from the difference between the energy of the photon, energy of radiations or photons of radiations getting to us or getting to the metal, minus the work done in removing the energy expended in removing the electrons from the atoms and away from the surface of the metal. So therefore, it means that our last question is trying to make use of the Einstein's equation, which says that E maximum, which we are looking for in this question, because they said, what is the maximum kinetic energy of the photoelectron, is equals to what? Energy of the photon minus the work function. From the question, the work function has been given. The work function was literally given as 3.04 times 10 raised power minus 19 joules. That being so, we can easily calculate the maximum kinetic energy which the electrons are accelerated from the cathode to the anode by just simply substituting the values here. We have that HF, the energy of photon, is 3 points up there in the second question, 3.96 times 10 raised power minus 19 joules, minus the work function, which is giving us 3.04 times 10 raised power minus 19 joules. That makes it easy for us to subtract. And then we'll have something that looks like this. 9.2 times 10 raised power minus 20 joules. Or better still, it will be 0.92 times 10 raised power minus 19 joules. The reason I changed it to standard form of 10 raised power minus 19 is because the energy we deal with in particle physics, such as energy of electrons coming from through electromagnetic radiation, are very small. And because of that, we don't want to deal with so much large or small numbers. We have to look for a new unit, which we call the electron volt. The truth is that an electron volt, which is written as 1 electron volt, the unit for energy of particles, is equal to 1.6 times 10 raised power minus 19 joules. With that understanding, you realize that the number of 1.6 times 10 raised power minus 19 joules that you find here will determine the value of the maximum kinetic energy in electron volts. But we are not going to do that now. That will be in another class. In fact, I have an assignment which I want you to run through. If you look at your basic physics textbook for senior secondary schools, exercise 5.3 and page 528, numbers 4C and 5Cs explains more about this concept, and then, in fact, ask you more questions on this concept. So if you practice them, I would love your feedback from such attempts. Thank you for your time.